Hello, welcome to another Leetcode video. So today we're looking at the problem nested list weight sum. So this is another problem that's asked by Meta pretty commonly, and this is a great problem to really understand recursion. So if you're trying to understand recursion, this is a pretty easy one to start with. So the question reads that we're given a nested list of integers nested list. So each element is either an integer or a list whose elements may also be integers or other lists. So essentially what this means is that we don't really have a predefined structure. We know we're given a list, but the elements could either be an integer or it could be a list. And then inside each of these lists, we could either have an integer or another list. So we could have these like arbitrarily nested structure like this where we might have lists going down to a depth of 50. So we might have something like this where we just keep going to get smaller and smaller lists and then eventually coming back up. So that's kind of what this is telling us. So the depth of an integer is the number of lists that it is inside. So we'll see here, the depth here would be 1 because we're only inside one list at this point. The depth of 2 would be 2 because we're inside this one list, but then also this smaller list here. Then likewise, this 3, we'd have a depth of 3 because we're in 1, 2, 3 lists. So what we want to do is return each integer times its depth and sum all of those up to get our final answer. So let's look at this example here. We see in this case we have our outer list with a depth of 1. And this is why this 2, we see a depth of 1 here because this is only inside one list. So here what we do is 2 times 1 equals 2, which contributes to our final sum. So here we have two other lists here. So in this first list, we see we have a 1, but it has a depth of 2 because this is inside two lists. So we'd have 1 times 2 equals 2. Same for this one, 1 times 2 equals 2, and this list is exactly the same. So we have 1 times 2 equals 2, 1 times 2 equals 2. So we sum these all up and we get 10, which is our expected answer here. So let's dive a bit deeper into this and see exactly how we could solve it. So this is a great problem to understand recursion. And if you're not familiar with recursion, recursion is essentially a function that will call itself. And how do we know that we can use recursion here, and what does that look like? So we're given this big list, right? We're given this outer list, and we want to do some operations on this list. So say here we have a 1, right? Well, we know that when we have an integer, all we need to do is to our sum just add some value, right? We can take whatever this is times whatever depth we're at, and that will give us some contribution to our final answer. But what if we had a list here, right? What do we do? Well, we could try to do a thing where like, all right, so we're in maybe some outer for loop. Maybe we could open another for loop to go through here. But then what if we have another list in here? We have to open another for loop and then another list in here. So you could see if we try to do this in an iterative way using loops, it becomes very, very complicated. It would be almost impossible to manage. This is where recursion comes in. So essentially, thinking that our bigger problem, we're given this entire list, right? Our input to our problem is one list. So if we see another list, this is kind of a smaller version of the original problem that we're given, right? So here we could have a similar thing. We could have a list that has an integer and another list inside it, which you'll see this subproblem here is exactly the same as this subproblem here. We're given a list with a 1 and another list inside it, and then this list has a 1 and another list inside it. So essentially what this means is that we have big problems, but within these we have smaller subproblems that we need to solve with the exact same logic. So because of this, this is why recursion is such a good choice here, because this problem by its nature kind of gives us larger problems with smaller subproblems inside them, essentially, that we need to solve. So what would this look like? So what's this look like for this problem? So say we're looking at 1 here. We know what to do when we have an element. We just need to add whatever its depth is, and our current depth being 1, and then take that, multiply it times our depth, and just add that to our sum. So very simple. But when we get to a list, this is where our recursion comes in. So essentially what we want to do is call this outer function that we've defined on this subproblem. So we'll have some function, right? And then we could say this is our new list. So let's pass in this list as our new nested list, right? So essentially, whatever logic in our function that we've defined for this outer list, we're going to use the same one for this inner list. So let's kind of walk through and see what happens. So now we go to 4. So we're at 4. This is an integer. We know that at an integer, we have to take it, multiply it times our depth, and add it to our sum. So here we see 4 times 1. Is that right? Well, I mean, according to this function, right, when we look at this list, we're at depth 1, but we know that as part of our larger problem, we're actually at a greater depth than 1. So what we have to do is we can't just rely on the function to let us know what depth we're at, because the function doesn't know what's happening outside. It always thinks that we're at depth 1 whenever we see an integer, because it only knows what it's passed in. So how do we keep track of the depth? Well, we actually add another argument to this function, which is our depth, right? So how this works is that, say we're at 1 again, we do whatever we do, then we come to this list, right? We see that this is a recursive subproblem that we want to solve. So what we do is we pass this list as our nested list, but whatever our current depth is, we're going to add 1 to it, right? So what this means is that in our next function, when we're going through this inner list here, what we're saying is, okay, go through this list, we're going to see 4, but then instead of multiplying this by 1, we look at our depth that we're passed in here. So we know that, oh, okay, our depth is actually whatever our previous depth was plus 1. So we know that this would be 4 times 2 that we're adding to our sum. So likewise, when we come to this list, we do the same thing. We know that our current depth is 2, right, at this inner list that we're in. So we pass in this as our new argument to our recursive function, and then we'll add plus 1 again. So at this point, our depth would be 3, which makes sense because we're inside 1, 2, 3 lists, right? So hopefully this made sense with all the recursion and how this works. I think when the code is actually seen, it'll make a lot more sense. So the time complexity here is O of n, right? Because we are going through each element 1 time. Even though we're doing this recursive function, we're only accessing each element at most once, so this is O of n. The space complexity is a little more complex. So technically, according to our problem, the depth can go up to 50, right? So we could have depths of up to 50 nested lists. So what does this mean for our space complexity? So when we do recursion, each recursive call we're putting onto a stack, which is called the recursive stack, and we're keeping track of it behind the scenes. But this adds to our space complexity because each function call that we do in recursion is put onto our stack. So potentially we could have up to a depth of 50 at one time. So that makes our depth or space complexity O of 50, which kind of cancels out, it's constant. So essentially what that means is that we could either interpret this as we have O of 1 space complexity because we know it's going to be at most 50, or it could be O of n, right? Because it's essentially maxed out by the max depth that we've seen. So there's a couple ways to interpret it. I think you could make an argument for either, but that's kind of the space complexity and how that works. So one other interesting thing with this problem is that we're given an interesting interface to work with, right? So we're given basically a class, this nested list class, and we have to use this in order to solve the problem. So most of this is not useful for our purposes, and I think this is on purpose. They want to give us this interface with a bunch of functions that we don't really need in order to kind of trip us up. So it's important to look at this and kind of see what we really need. So we have a bunch of functions. So we have is integer. So this is going to allow us to, on any element that we're looking at, we can call this function to see, is this an integer? This is something we definitely need to use because we need to, our whole crux of this problem is knowing if something is an integer or a list. So we definitely need to use this in order to identify if we're looking at an integer or a list at any point. Another one is add, right? So what this would do is essentially add an integer to a list. Well, our test cases are predefined. There's no reason for us to ever do anything like this, so we can safely ignore this. We also have set integer. Again, this is not something we need. Our test cases are already predefined here, so there's no reason for us to ever be like using this function to do anything. We also have get integer. We can use this. I don't think it's totally necessary, but we can use this to get the value of an integer, and then get list. So get list is a function that we do want to use because when we're looking at a list, we need to get that list to be able to pass it into our recursive function. So hopefully this made sense. Let's hop over into the solution and see exactly how it works. So the code here is actually very simple. So what we're doing is we're defining this recursive function. So this is the function that we're going to use where we're going to pass in lists, and what it's going to do is tell us if what we're looking at in the list is an integer or a list, and then handle the logic from there. So we start our answer as 0, and this represents the answer at the current depth that we're looking at. So what we do is we iterate through every element of the list, and if that element is an integer, we know what to do. We know that in an integer, we just take that integer, we get the value, and we multiply it by the current depth that we're at, and that contributes to our answer. Otherwise, if it's not an integer, it must be a list. So what we do here is what we say is we do this recursive call. We say to our answer, we want to add the result of this recursive function, and what we're passing into the recursive function is the current element get list. So we know that it is a list, so we can call this get list to actually get the value of the list, and then we pass in depth +1. And remember, because we're entering another list, we need to keep track of the current depth that we're starting at for that list. So that's why we take the current depth that we're at and we add 1. Then at the end of our recursive function, we just return the total answer that we've calculated for this level. So then finally, at the end, in our outer function, we're just going to call that recursive function with the original nested list that we're given and an initial depth of 1. So let's submit, and it works. So this is another pretty good meta tag problem. If you're trying to learn recursion, I definitely recommend this one. It's pretty simple recursive logic and doesn't need a ton of code. So hopefully this was helpful, and thank you for watching.